All right. Well, good evening, everyone. It is 5 p.m. Eastern Time. And in the interest of keeping everyone on schedule, I'm going to get started. And I'm going to spend the next 7 to 8 minutes just talking to you all about the story behind BrainX and why we're here today. Again, this is by virtue of introduction, this is July 2021 session of the BrainX Community Live. And this is the BrainX Community. Someone would ask me, what do five physician scientists do when they get together? Well, they come together and they say, we want to make a group that talks about big data, research, education, machine learning, artificial intelligence. And we really want to be a conduit or a channel that helps with the clinical applicability of all that is being done in all of these domains. And yes, innovation like art is never perfect, and we're still in the process of innovating. So we will get to perfection at some stage. Very quickly, I wanted to introduce all of us. You all know me. Then there's Piyush Mathur, Jacek Savinsky, Kamal Maheshwari, and the one and only Dr. Frank Pepe, whose middle name should actually be face transplant, but he refuses to adopt that middle name. I won't go into too much of a history about us, but this is our brainchild. We thought about this about 3 years ago, and I'm glad that today we're here talking about things that make clinical sense and relevance to all of us. So what are we doing with the BrainX community? We are really talking about machine learning in healthcare for the good of all. Like I said, we've had 3 successful years. We're an online community, 3,000 plus international members and growing. The website links are on here. We have a LinkedIn group, and we have monthly BrainX community sessions and much, much more, as I'll talk to you about. This is what the BrainX community website looks like. We're going to have a fully revamped and re-engineered website in the next month or so stay tuned for that. What can you do with the BrainX group? You can interact with us. These are pictures, obviously, from the pre-COVID era, back in 2018, when we first started having some of our interactive sessions. Here is one where we've talked about, say, applications of AI in oncology and gastrointestinal diseases. And we also have a YouTube channel where we record a lot of our sessions, so people can go in and look at all of these sessions at their own leisure. And we have social media networking through our LinkedIn group, the BrainX community. Just go on there, express your interest to be included, and you'll be on there before you know it. Nearly 2,000 plus members on the LinkedIn group as well. What all do we do with the BrainX community? Resources on the website itself. We have a list of curated articles. These articles are linked by category, so you can search, say, in a certain area of interest without too much of looking around. And our hope is to make things easier for you. It's way easier than scanning things over a PubMed search. We also have links to freely accessible data sources from the NIH, from other entities such as Mimic or EICU or other clinical centers of excellence. We have COVID-related data sets also available. And then we're collaborating across the world. Here is one of our collaborations with our European colleagues who are bariatric surgeons. They're helping us with their group of engineers. We have the ability to look at journals. We curate articles and put it on the BrainX community website for everyone to see. And this is another example of one of our collaborations with a group in Delhi in India, where we looked at, we reused their data scientists who worked with us to look at determinants of COVID-19 mortality in the United States. And very finally, or last but not the least, we have BrainX Talks, which is sort of my baby, so I'll take credit for it. It's a podcast that we started through BrainX, and every month or so, I interview someone who wants to do more with artificial intelligence in healthcare, whether it be a data scientist, or a physician or a pure scientist who does basic research. And we put them out on Apple iTunes, Google Podcasts, and Spotify. So please subscribe. I promise won't disappoint you. It's a lot of entertainment, a lot of just freestanding conversation, and truly healthcare and AI for everyone. We also put on a year in review publication. This is our last one that went out. We collaborate with a group of experts around the world who help us curate a set of articles, and then we publish this in one of the open access portals. Even though it's not peer reviewed, it's an easy way to get through to what you want in terms of if you're looking for a certain set of knowledge areas you want to investigate further. And that from our last publication, the 2020 year in review, as you can see here, anesthesia and critical care, in terms of the number of publications relevant to artificial intelligence are sort of doing okay, but they could actually do much better. What's really leading way ahead of everyone else is radiology, and we well know that imaging comes with a natural set of artificial intelligence learning and data points, and clearly we need to learn from our colleagues in radiology. We have a lot of catch up to do as far as anesthesia and critical care is concerned. And so in a nutshell, this is BrainX Community, brainxai.org as our landing website, brainxcommunity.com for the community education page, our LinkedIn group, our live session, part of which is going on live right now, our YouTube channel, our podcasts, and then down below is the email for the founder of the BrainX group. That's Dr. Piyush Mathur, who's an intensivist and anesthesiologist at the Cleveland Clinic. So without further ado, I will sort of introduce our speakers. I probably won't do full justice to their abilities and what they have done in the field of artificial intelligence. But let me start by saying that it is a matter of great honor and great pride for me today to bring out speakers from my own institution, the Wake Forest University School of Medicine. Our first speaker is Dr. B.Scott Segal, who is my chairman, and he is a professor and chair with the Department of Anesthesia here, and also the Enterprise Academic Department chair for our Atrium Health System. And following Dr. Segal will be Khalid Niazi. Khalid is a PhD and an assistant professor with internal medicine and the Center for Biomedical Informatics within the graduate school, the School of Medicine, and the Wake Forest Baptist Health Network. And these two gentlemen are going to talk about something that is very applicable for not just anesthesiologists, but I believe for the general betterment of mankind, is how to recognize difficult airways by not just asking you to open out your mouth and stick out your tongue, but to do more than that, and to use advanced imaging and artificial intelligence, and where we are today and where we can go with it in the future. However, as I let them take the podium, let me have a quick story about each of them. Now, here's my story about Khalid. And you might say, well, why do I have a coffee cup with Wake Forest University on it? I first got to know Khalid because he taught me last year. I'm part of a master's program at the graduate school where I do a master's in clinical research, and Khalid taught one of my courses there in biomedical informatics, where he taught advanced image analysis. So thank you, Khalid, for all your teaching. It was really, really complicated. And I'm going to say that I learned a lot from you. And then Dr. Segal, who has truly, taken our Department of Anesthesia sort of the next level when it comes to perioperative outcomes research. And he has inspired me so much with biomedical informatics that I am ready to do the boards with with clinical informatics very soon. Again, inspired from him because he is certified in clinical informatics. So here we are. I'm going to give them the center stage, and I also want to thank our wonderful research team We are a group of nearly 15 clinical research technicians and research nurses who are working to set up our advanced center for perioperative outcomes research. So anyone who's watching who wants to work with us, come to Winston-Salem and we'll get the job done. Dr. Segal, it's all yours.
Afternoon, everybody. Thanks for having me. Let me see if we can get the sharing thing working here. You see some slides now? Okay. Thanks very much for the incredibly generous introduction, Ashish. It's a privilege to have you here. We were fortunate enough to recruit Ashish a few years ago. He won't toot his own horn, but he's built quite a clinical research enterprise here. When he came, we had a pretty nascent group, and now we keep that large team you saw busy, and we keep adding more and more work to the point that we're going to need more and more people and space to house them, and that is in very large measure due to Ashish's hard work. He was also recently promoted to vice chair for research in the department, a title well deserved. So today we're going to talk a little bit about our work in using artificial intelligence techniques and image processing to evaluate the airway, in particular with regards to endotracheal intubation, but perhaps more broadly in the future in a number of other outcomes. There seems to be a requirement that we tell you a little bit about where we're from. This is a nighttime view of the skyline, such as it is, of Winston-Salem. Kind of an attractive picture, but shows you that we're a small to medium-sized town. I want to tell you we're famous, unfortunately, for a few things, like being the world headquarters of R.J. Reynolds Tobacco, Hanes Brands, which makes lots of underwear, and Krispy Kreme donuts. This is a Krispy Kreme donut double cheeseburger that you can get at our fair. This explains why the hospital's always full. And if you combine that with the cigarettes and the underwear, it makes quite an image in your mind. And I'll let you just ponder on that a little bit while we continue. A couple of quick disclosures here. I hold with a co-investigator from my days in Boston a patent on some early work in this regards. They're the owner by assignment is Partners Healthcare in Boston. Dr. Niazi and I have a utility patent application, but not a patent yet, and the owner by assignment is Wake Forest. We have no licenses or other financial interest in any of those projects, and you see some of the grant funding from the Wake Forest CTSI, the Anesthesia Patient Safety Foundation, and the National Institutes of Health that help support in part our work. All right. There's probably nothing more emblematic about the specialty of anesthesiology, and I apologize for those of you listening who are anesthesiologists, but maybe for some of you who are not, than to say evaluation of the airway and management of the airway is probably the most emblematic procedure that we undertake. And while I will not review this entire topic for you, I will touch briefly on these questions about airway evaluation in order to outline the clinical problem that Dr. Niazi and I are trying to come up with better solutions for. It is almost certainly Airway Management 101 to assess the airway. These are some quotations from the American Society of Anesthesiologists Task Force on the Management of the Difficult Airway. And they make some statements like this, that although there's insufficient literature to evaluate the efficacy of doing a history, it's obvious that it's a good idea. And while there's insufficient published evidence to indicate any one feature matters, they go on in the bold at the end of this quote to say an airway physical exam should be conducted whenever feasible before initiation of anesthetic care. There's not an anesthesiologist that wouldn't try to do this, at least at some level for every case. But unfortunately, it doesn't work very well. And most difficult airways are in fact unanticipated, even with current techniques. In a large observational study in Denmark, Norskov reported a few years ago, close to 200,000 patients, using quite a strict definition of a difficult airway that yielded about 2% of airways being difficult, that 93% of those were unanticipated by modern techniques. Using more liberal definitions of difficulty, still 75% were unanticipated. It's one question that is worth asking is what exactly are we trying to predict? And I'm going to say that we're probably not trying to predict truly failed intubation where it's impossible. That's a really rare event, fortunately, in the modern era, 1 in 2,000 or 2,200 in the general operating room, perhaps more common in obstetrics. In the National Audit Project 4 in the United Kingdom and a 12-month prospective audit now a little bit more than a decade ago, death or brain damage from an airway disaster was about 1 in 20,000. And certainly those catastrophic events vary over time by operator, by institution, by the patient population, by the clinical situation. Difficult intubation, there are many, many definitions that vary, again, by the study, by the anesthesiologist or other operators, by their experience level, and by the definitions of what you want to call difficult. The overarching kind of agreed upon rate of this is somewhere around 5 or 6%, with quite a wide range there, as you see in Shiga's review of a bunch of studies. It varied between 1 and 18%. Using somewhat more liberal definitions and more complex populations, it may be twice as 3 times as high. Intubations done outside of the operating room setting are also considered to be more frequently difficult, perhaps because of the clinical situation or the operators involved, at about 10%. And there are a number of specific clinical definitions. We'll take a quick look at some of these by way of review in a moment. But there are many ways to define it, and obviously having a clear endpoint is part of training ourselves or certainly any computer network. This is perhaps one of the most common views. Most of the people who are anesthesia background on the listening will know about this, but just to remind you, these are the Cormack and Lehane grades of the view of the larynx during direct laryngoscopy. We would all like to be here in the upper left-hand corner of the picture. This is a grade 1 view where we see the epiglottis, the full extent of the vocal cords, and the posterior arytenoid structures fully visible, and it's quite easy to pass an endotracheal tube between the vocal cords. This is a grade 2 view. Some people divide this into 2A and 2B, where only a portion of the glottic structures are seen. A grade 3 view here is one definition of difficult, where no structures of the glottis itself are seen and only the epiglottis is seen, or a grade 4 view, which everyone agrees is difficult, where no glottic structures at all are seen. So typically we'll define difficult as grade 3 and 4 together, or sometimes just grade 4. And there's lots of different ways you can actually do it. I'm not going to presume to try to teach everybody all of these different techniques, and many of you know them all very well, probably better than I do. Almost everybody does the first 3 things on this list: ask about a history of previous difficult intubations, which is very specific but poorly sensitive. That is, if it's easy in the past, it's usually easy in the future, but many, many difficult intubations are not preceded by another one. And oftentimes, if we have a history of difficult intubation, we're going to change what we do so we will not encounter it again. The Mallampati class is a view of what is visible when you open your mouth and stick your tongue out, as Ashish showed us just a moment ago. You do this. Ideally, you'd like to see everything going all the way back and seeing the entire uvula, the soft palate, hard palate, and the posterior pharynx visible here. Beyond the uvula. That would be a Mallampati 1. This is a modification of Mallampati's original 3 scores. There's 4 in this. This is a Mallampati 2, where only a portion of the uvula is seen. Mallampati 3, where only the soft palate can be seen, the uvula and posterior pharynx are not seen. In a class 4 airway, where only the hard palate can be barely visualized. Usually, these grades are indicative of more difficulty. And then there's the thyromental distance, which measures the distance in the extended head between the thyroid cartilage and the tip of the jaw. These 2 together are thought to be the best clinical tools right now, but we'll see in a moment just how good best is right now. There's lots of other things that one can do, other distances one can measure, other maneuvers that can be measured, and I won't review all of those now. The question is, do they work? And the answer is not very well. And that is why we're here. This is a review by El Ganzouri of about 10,000 patients who were prospectively examined using a number of different airway examinations and looking at either grade 3 and 4 or grade 4 views of the glottis as a difficult airway. And what you see is that the sensitivity of these tests are pretty poor. If I blow those up for you, this is the classic Mallampati test of a Mallampati score of 3 on a 3-point scale. So this would be the worst on the Mallampati scale, having sensitivities only about 40 to 60% and specificities a bit higher. Even combinations of these tests perform relatively poorly. And this is a prospective study in about 500 folks showing that you can combine these tests and get much better specificity, but sensitivity obviously decreases as you do, to the point that you're only picking up a small fraction of the difficult airways if you insist on all 3 tests. This is a meta-analysis of a number of different studies. I think it's about 35 studies and about 30,000 patients taken together, looking at a wide variety of clinically used tests, including the combination of Mallampati and thyromental distance down here in the third from the bottom row, which was thought to be the best of the available tests with a positive likelihood ratio of nearly 10 and a negative ratio of 0.6. Ideally, you'd like to be over 10 and under 0.1, but this is pretty good performance. But you can see that the overall sensitivity was about 36% when meta-analyzed across the trials, specificity a bit better at 87%. These are receiver operating characteristic curves of the different tests involved in the study. And the best was here, again, the combination of Mallampati and thyromental distance with an area under the curve across multiple studies involving thousands of patients of about 0.84, which is maybe not terrible, but we would certainly like to avoid false negatives. That is, we don't want to be caught unprepared for a difficult airway by assuming the airway is going to be easy when it isn't. Conversely, we don't want to prepare for a difficult airway all of the time because those techniques are expensive, time-consuming, and in some cases uncomfortable for patients. We'd really like to see a much tighter area under the curve than this clinically assumed best practice. Now, people have tried to combine in various arithmetic ways, generally linear combinations of a wide variety of these measures, with the idea that all of them measure something, so maybe putting them together might do well. And a number of attempts to do so are illustrated on this slide. Again, I won't walk through all of them, but these are basically arithmetic formulas that try to regress various things to get to a better prediction. And you can see that there's early promise when you look at the area under the curve here. Some of these have areas of in the 0.8 to 0.9 range in various combinations of different factors. However, these all failed in a large cluster randomized clinical trial, again from Norskov from Denmark. This was a big multi-center study with 28 institutions and about 64,000 patients. Each center was randomized in a cluster to either usual care, which is typically Mallampati and thyromental distance and clinician judgment, versus a simplified airway risk index, which was essentially the El-Ganzouri index of multiple factors that I showed you a few moments ago. And the incidence of unanticipated difficult airway was 2.4% in SARI departments and also 2.4% in usual care departments, with an odds ratio obviously not different. So these studies, although they can sort of work in a derivation validation set sort of arithmetic combination, they don't seem to actually improve clinical performance in the real world. And it doesn't seem to be getting any better. This was a review article in the Journal of the American Medical Association late in 2019 that basically concluded, although there are several clinical findings that are useful in predicting a higher likelihood, no clinical finding reliably excludes a difficult intubation. So that was kind of the state of the art. And now I'll tell you just very briefly how we got started on this whole idea of trying to use computer vision and machine learning to do a better job. I'm going to tell you, and this is a bit of a politically incorrect story, so I'm going to just sort of apologize in advance. But when I was a resident and then a young attending back in my days, back at Brigham and Women's Hospital in Boston, there was kind of an old timer anesthesiologist who had been around really forever and was absolutely a master with a laryngoscope. He could intubate anybody. And he did it without all the modern fancy tools, certainly before video or any of those sorts of things. He was just very, very good at what he did. And he used to say, you know what, here's how you know. If the patient is good looking, they're easy to intubate. I told you this was politically incorrect. So there's a bunch of celebrities' faces. If you think about it though, there is actually something to this non-PC comment, and that many of at least the Western ideals of beauty in the human face are probably in fact features that are correlated with an easier intubation. Things like a high cheekbone, a long, strong jawline, lack of obesity, a clearly defined neck, and perhaps the ability to move the head freely. If you asked any experienced laryngoscopist, do these folks look easy to intubate, they'd all answer yes. We have a subjective gut feeling, perhaps educated in part by these imperfect airway exams, but clearly a subjective sense of what makes an easier and difficult airway just by looking at the appearance of the face. In some data that I won't show you today, we proved that that was the case by giving people either photographs of the face along with the Mallampati and thyromental distance, or just the Mallampati and thyromental distance, and people's ability to predict who would be a difficult airway was in fact improved just by giving them the pictures. So there's some information in the anatomy of the face and the appearance of the face that does in fact correlate with difficult intubation. And now we're going to begin our journey in exploring some of the machine learning techniques. Now, more than a decade ago, my collaborator, Chris Connor, and myself back in Boston hypothesized that human observers are using these cues and that we would try to see if we could teach a computer to use similar cues. So we derived a predictive model based on photographs of the face. At the time, we used a proprietary computer program that would take a picture of the face. This is Chris Connor in bilateral profile views and a frontal view. And you could feed these images into a program called FaceGen Modeler that was based on some technology developed at MIT in a project called the Eigenfaces project, which used high resolution scans of people's faces, about 300 subjects, to help develop an algorithm. And using an iterative algorithm that took several minutes to solve for a given set of images, the computer would derive a computer model of this face. Now, again, this was a relatively older piece of software. It required the placement of several fiducial markers, shown here on this image, into key spots on the face by a human observer. So one had to label the features of the face with these little green markers so that the computer could get a head start on trying to model the face. And then over a series of minutes in an iterative sort of process, it would derive a mathematical expression of the face that was actually underneath it all, a single point in a 50-dimensional eigenspace, which it then translated into an image. And the image on the right is the mathematical model of Chris Connor shown on the left. And it looks a lot like him, doesn't have all of the texture features like hair and so forth in there, but is a reasonable, I think more than reasonable, facsimile of his facial appearance. Underneath it all, those 50 eigenvalues actually were projected to these 61 descriptive terms to make it a little easier for humans to understand them. And what we did is we tested each of these as a univariate predictor of difficulty in a prospectively measured set of 40 patients, 20 easy and 20 difficult. And we took any that had a p-value of less than 0.1 in a univariate analysis, shown here in the red boxes, and entered those variables into a series of logistic regressions where we exhaustively tried all of the combinations, so 2 to the 11th minus 1 different models. And the model that was selected is the one with the best area under the rock for the derivation set. And then we validated it in another set of 40 subjects, 20 easy and 20 hard. And we took the model to avoid overfitting that had the best product of the area under the curve in both the derivation and validation sets. And it really just had 4 values shown here. And thyromental distance made the model. And you'll note at the bottom, Malin potty class did not make the model. Even if we forced Malin potty class into the model, it did not improve performance. But these 4 variables did actually perform quite well in both our derivation set and our validation set and the combined set. In the combined set of all of the airways, it correctly predicted 70 out of 80, or 87.5% of the faces. And if we took only those that were even more difficult, that is, they had an intubation difficulty scale greater than 5, which is a research tool based on a number of factors other than just the laryngoscopic grade, it got even more of them right, 89.2%. And the sensitivity and specificity were quite high, 0.96 and 0.85. By contrast, and we corrected this using Bonferroni correction, dividing the raw p-value by 1,024, 2 to the 10th, based on the number of tests. And these are very highly significant fits. And it worked. We could sort of engineer a face that the computer model would say is the most easy face it could imagine, if you will. And this is what it looked like. This looks like some of the beautiful people on the slide before, I think. Notice the high jawline, the high cheekbones, the well-defined jawline, etc. And this is the model that it considered would be the hardest airway. And although I can't tell you if it's actually the hardest airway, it certainly looks a lot harder to anybody who's actually managed airways before. So it passed, if you will allow the pun, sort of a face validity kind of test. It really seemed to pick up on features that really made a difference. I will also point out that in our test, Malin potty and thyromental distance alone or in combination barely performed better than chance compared to the model in our performance. However, in a prospective trial of about 500 subjects where we applied this model to the same faces, measured in the same way, and calculated the machine algorithm's prediction versus the ground truth, the model failed to replicate. It did marginally outperform Malin potty and thyromental distance, but it didn't come even close to the original performance, getting really just a bit over 50% of them right. And I think this highlights some common problems with AI in general and with machine learning around images, perhaps more specifically. The first, I think, is that replication is critical. So we did this pretty carefully with derivation and validation sets and took great pains to try to avoid overfitting, but they can still be overfit. So it is now pretty much de rigueur in these kinds of studies to have a third test set completely independent of the derivation and validation sets. In addition, we trained this model on a very small number of subjects, just 40 subjects, and the size of the difficult airway space, if you will, that is all the different ways that airways might be difficult, might be much vaster than the ones that were representative in the model that we used. In addition, our model was a supervised model in the sense that we had to have human input both into the fitting of the faces to a computer model, that is, we have to put the fiducial markers on manually, as well as in the actual derivation, which was through exhaustive sort of brute force logistic regression rather than any sort of model that could learn and get better. But the good news is that the field has been advancing truly at light speed. The field of image processing, facial image analysis, and modern views of developing convolutional neural networks that are much more sophisticated than the program that we started with. And that's going to be Dr. Niazi's cue in just a moment. My last slide is here. and this would be otherwise after what Dr. Niazi tells you about some of our early successes, but I'll point them out now, is that even if we are successful, we still will have some problems. One is, and this has gotten a lot of press lately, and that is there is known bias introduced into particularly even facial analysis by a lack of diversity in the training set. So it will be critically important that anything we develop be absolutely trained on and then tested in a diverse pool of faces with different ages, different sexes, and different ethnic or racial identities. There's also what I think some clinicians would call the black box problem, and that is, suppose we build a model that you take pictures with your phone and it gives you an answer and it's right a lot. Will clinicians actually trust it and rely on it if their own judgment is different? I think this begs a bigger question of who might actually use this technology. And it may not be airway experts, right? It might be those who only occasionally manage airways, or even outside of a traditional healthcare setting, such as on a battlefield or in an ambulance and so forth. I do also hold out some confidence that even though this will be something of a black box, that it may be possible to eventually develop the trust of clinicians. And I'm buoyed in this sense by our ability to trust monitors like the BIS monitor for determining the depth of anesthesia of a given patient, or pulse pressure variation monitoring, which, although we can theoretically manually print out an arterial line tracing and measure this ourselves, we usually just rely on a dimensionless number to tell us whether the patient's fluid responsive or not. And we've all, most of us anyway, have grown to trust such measures. And so I have some faith that with enough time and positive results, we might be able to overcome this black box problem. And then finally, and I think this is important, is that just as airway evaluation and image processing and all that other sort of stuff are advancing, so is the ability to manage difficult airways. And one realistic question is, will improving modern airway management tools make the problem less relevant? I certainly hope that we're fast enough to be relevant by the time this is completed, and we're not going to be usurped by tools that make us obsolete. And that concludes the statements that I will be making about why we need to do better. And I'm going to now pass it off to my colleague, Khalid Niazi, to tell you some of the work that we're pursuing to try to do just that.
Thank you so much, Scott, for laying the groundwork. You have made my job pretty easier. Thank you, Ashish, for the generous introduction. So, can you guys see my screen?
Yes.
Great. So what is the potential solution? So the solution which we have is basically based on computer vision and machine learning. But before I go into that, here is the team, which is the most important thing for this project. So Thomas Tavalara and Ziyu, they are the foot soldier for this project. We have Shelby, who is working on the app development part of this project. We have Dr. Metin Gurjan, who is providing us with the computational resources, and Scott Segal, you just heard him. Basically, this is his brainchild. So as Dr. Segal has already said a lot about difficult intubation, I'm not going to spend too much time on it, just one slide. So there are 150 million intubations performed each year, and then 75 to 93% of difficult intubations are unanticipated, and they are unanticipated because the clinical tests we have, they are not good, or they perform modestly. So for instance, the sensitivity of a Mullen-Berry test is 32.5. Basically, sensitivity means here that the ability of a test to correctly identify difficult to intubate patients, and 85% specificity, which is basically the ability of a test to correctly identify healthy patients. So we definitely need better tools to perform, to identify these patients. But there are some challenges. So one of the first challenges that we have limited data sets. And if we are trying to solve this problem through imaging, and in imaging, deep learning is right now the most up-to-date tool, which can essentially perform anything at the moment. So if you want to use deep learning is extremely data hungry. And then, as I said, I mean, we don't have like access to thousands and thousands of images. So it's a problem for us. And if you're trying to perform classification, and when I say classification, for instance, in our case, we can say like we can classify the patients into difficult and easy patients. So basically, if we are trying to perform classification using deep learning, we have to do two things. The first thing is basically the automatic feature extraction. And the second thing is that we have to somehow pass these features through a classifier and then perform the classification. Basically, it's the feature extraction part, which takes a lot of images. So you need to show the system a lot of images to learn meaningful features from the images, but we don't have that luxury. So we have a total of 77 difficult intubate patients. So this data, this number 77 is pretty old. Basically, it's from last year. So we have been recruiting patients. Right now, we have close to 200 difficult to intubate patients. So this data set is increasing, but I haven't updated the presentation yet. So the results here, they are like a year old. So what is the potential solution if we have small data set? One is that we can do transfer learning. Those of you who are familiar with deep learning, this is pretty a standard procedure. What you do is you extract features from one domain, and then you apply those features to another domain. So essentially, you're extracting features from one data set, and then you are saying that, can I use the same features in another data set to perform a classification or regression or another problem, to solve another problem. So there are three big networks when it comes to transfer learning. One is the ResNet family, the other one is the Inception family, and the third one is AlexNet. So all three were trained on millions of images. And when I say millions, I literally mean millions of images. And what they can do is they can extract features from classes like cats, dogs, and other things, cars. And once you have those features, what you can do is you can say like, okay, well, these features are pretty generic. I can apply it on another domain. The domain could be medical imaging, or it could be something else. So this is used pretty exhaustively. Right now, there are quite a few papers, thousands and thousands of papers using these different pre-trained networks. The problem is that when we try to apply these ResNet, Inception, or AlexNet, and then we slice and dice these networks in many different ways, when we try to apply it on our data set, the results were as good as a flip of a coin. So they didn't generalize at all. So they were pretty bad. And we realized that the features which they are extracting, they're not meaningful, or they're not powerful enough to differentiate between these facial anatomies. So we thought that it might be more appropriate if we go the route where we are extracting features from facial databases. So we did that. So I'm going to talk about it in a minute. So we are doing transfer learning, but the transfer learning is that the model, instead of using a pre-trained model, we are creating or generating a model of our own, and then we are doing fine-tuning our own data set, and then this is how we are using it. So I'm going to talk about this in a minute. So the second challenge is that when you're performing a classification, we generally have a label. For instance, we have an image to the right, and then for this particular image, we might have just a label like, it's a difficult patient or an easy patient. Let's assume this is a difficult patient. So if the algorithm predicts that that the label is difficult, is it good enough? Can I tell my colleague that the algorithm is saying difficult, so will you accept it? And most of the time, the answer is no. And the reason is because the algorithm, if you perform like, I don't know how familiar you are with these deep learning methods, but let's say we are doing these class activation maps, which are essentially telling you like which areas of the image are contributing or driving the classification process. If you do that, sometimes, for instance, in this image, it might start to pay attention to the background or the hair or the pillow or the gown, which are completely irrelevant areas. So the problem with classification is that, and if you have smaller data, that is like a huge problem, that it starts to pay attention to areas which are irrelevant. So as a consequence, it failed to generalize. So when you start to do like, start to use it on a different data set, it is hard for it to generalize there. So one of the potential solutions is that we can automatically identify landmarks, and extract regions around them. So let's say we are extracting eyes, nose, ears, and all these things as Dr. Segal was doing like 20 years ago. So if we do the same thing automatically, we might be able to find a way around this problem. Like, I mean, the classification problem where the deep learning systems start to pay attention to irrelevant areas. So we can avoid that because all the areas which we are putting in, they're all relevant areas. So here is the method. So there are 6 steps, although it looks a lot, but trust me, it's not a lot. So the first step is that you have to download this web face, which is basically a celebrity database. And then it's followed by landmark detection. So for each image in this database, we perform a landmark detection, which is followed by face alignment, because not everybody is looking towards the camera. And especially in this particular database, everybody's posing in maybe towards the right or the left, sometimes even in the front. So we have to perform some sort of a face alignment. As a human being, we can compensate for those alignments, but for a computer, it's really important that we do that. And then once we have done the alignment, we go in and then perform the region extraction. And then what we do is for each region we have extracted, we train a neural network. And this is followed by multiple instance learning. So I'm going to go through each of these steps in detail, some sort of a detail. So this is basically step 1. Basically, you have to download this database, this celebrity database. It's a database which contains over 1.2 million images of more than 10,500 celebrities. And it was originally developed for face recognition. So you can use it to identify, so you can train a model using this database, and then you can maybe do transfer learning to do some face recognition application or stuff like that. Okay, so once you have downloaded that database, what you need to do is you have to identify these landmarks. And then when I say landmarks, we are using, thanks to a lot of good work in deep learning, especially in facial recognition. So we are using this DLib. This is an open source, and it identifies like 68 fiducial landmarks automatically. So you don't need to do much there. So once you have identified these landmarks, what you need to do is you need to perform face alignment. And then the reason why you need to perform alignment is pretty obvious here, that the Bruce Lee is looking in a different direction and then he has some sort of a pose. So we want to make it like rotation invariant and scale invariant. So the way we did is that we took a couple of points in the inner eyes and then the bottom lip, and then we try to align everything according to those 2 lines. So the first row is showing basically how, if you try to align it with inner eye, so there are a couple of points here, inside the eye, and then you have at the bottom lip. So you draw these lines and then you try to make them horizontal and vertical. And this is how the image is basically aligned. And you do the same with another method where you're using the outer eyes and the nose. And the second part, the second row here is showing that, like, if you try to use the outer eyes and the nose, the alignment looks like this. And I'm going to get to it why we are doing the alignment in 2 different ways. The next step, which is basically the 4th step, is region extraction. Once you have identified, once you have rotated the image, what you need to do is you need to identify different landmarks. One is the eye, nose, mouth, chin, bridge, cheek, jaw, and neck. And then you take like 11 regions from here. So I have shown an example here where you can see that the first one is you're extracting the left eye, and then you're extracting the nose. So the images are basically cropped like this. So all this is based on the initial fiducial landmarks which we have found. So we just extracted regions from it. So now comes the interesting part. So what we do is we take the eye and we train a CNN. And this CNN is basically trained to identify a person based on just the eye, left eye. So we collect all eyes, left eyes together, and then we train a CNN. And when the question we are asking is, can we identify the 10,500 celebrities just based on the left eye? We ask the same question for the mouth, chin, and the nose. And The good news is that once we have done that, we managed to get an accuracy over 70%. So 70% of the time, we were able to identify the correct person based on these networks. So these are really amazing results because we are looking at a chin. So whatever feature the method is learning, this deep learning method is learning, they are powerful enough to differentiate between 10,500 guys. So this was really amazing. So when we looked at these features, that these are super useful, super strong features, what we did is we replaced the last layer with, instead of asking it to differentiate between 10,500 celebrities, we asked it to differentiate between easy and difficult to intubate patients. So see the switch again. So we started with simple CNN, which is good at identifying different people based on these different anatomical landmarks. And then we replaced the last layer with just easy and hard, which is easy and difficult to intubate patients. And we are not changing anything else about this network. So the network is pretty good at identifying differentiating between celebrities. So we check if it can differentiate between easy and difficult to intubate patients. And the answer is yes, it can do that. So this is basically our model. So we started with the celebrity database. When we did that, we overcome the issue of features which are relevant to fiducial landmarks. So we extracted features which are not like features coming from cats and dogs and other things, but I mean, they are like fiducial features. So when we started using these fiducial features, we realized that it is something which we can use to differentiate between easy and difficult to intubate patients. So this is basically the second last step. And then the last step is that once we have these models trained, so we have a total of 11 regions. I'm just showing 4 here, just for the sake of an example. So we have an eye model. It is saying it's an easy patient. The mouth is saying it's an easy patient. The chin is saying hard. The nose is saying easy. One of the easiest way to combine these things is the majority rule. So because we have 11 models, it's always going to be, I mean, we can easily break the tie. It's an odd number. So here, there are 3 models which are saying it's easy, and the 4th one is saying it's hard. So because the majority is saying easy, we're going to put a label of easy. And this is not the only thing. What we can do is we can go back and then pinpoint the area which is basically contributing towards that decision. So basically, we can tell like which part of the chin is driving this decision. All right. So this is one way of doing it, which is pretty simple. You do the majority rule. The other way is that you can use multiple instance learning. What multiple instance learning does is it takes features from eye, which are basically here, and then the mouth, the features are here, and then chin, the features are here, and then nose, the features are here, and then it learns an aggregation function. And then the aggregation function is basically what should be the contribution of the eye feature, the mouth feature, the chin feature, and the nose feature should be, and then what should be the ratio of it, and then it combines it, and then it arrives at a decision. So that is like a more fancier way of doing, combining different networks. So I'm going to get to it in a second, and I'm going to show you some results based of that as well. So here is an experimental design. So we have a total of 500 patients, 429 easy, 77 difficult, and all these images are frontal facial images. We have performed 10-fold cross-validation, and then for a comparison with the clinical test, we have compared it with Mullen-Petty score and thyromental distance. I think the spellings are wrong for Mullen-Petty. Anyway, so the clinical outcome is a ground truth. Dr. Segal has already talked about the clinical outcome, which is basically after the surgery, we know like for sure what should be the outcome. So here are some results. So this is based off when we are combining the CNN based on the majority rule. So there are 3 sets of results here. This one, the first one is in eye bottom lip, which means that we use the inner points inside the eye and the bottom lip for the alignment purposes. So these are the results for that. And then we are reporting the results in terms of sensitivity and specificity. So when you combine all these 11 models, your sensitivity and specificity are pretty decent. is close to 70%, and then the specificity is close to 64%. If you use the outer eye and the nose for alignment purposes, and then you see the sensitivity and specificity, it is close to 64% and 59%. And if you don't perform any sort of alignment, it is close to 68% and 61% for specificity. So those were the results which we got for majority voting. How does these results compare to the clinical test, Mallampati test, and thyromental distance? So the sensitivity and specificity, they are pretty, I would say, even. So whenever the sensitivity and specificity, they are not like matching each other, it means that the system is suffering from overfitting. So here you can see, like in Mallampati test, the sensitivity is 35%, which means that you can hardly identify difficult intubation patients. But I mean, when it comes to specificity, which is basically saying that how easy it is for a person to identify healthy patients, that is pretty high, which is 78%. Essentially, I mean, if you call every patient as a healthy patient, your specificity will go high. The idea is that we have to find a balance between specificity and sensitivity. That is like an appropriate model. So if you look at the thyromental distance here, the sensitivity is close to 88%, which means that if you start calling every patient as difficult, you're going to get like 100% sensitivity. But when it comes to specificity on our data set, this is close to nothing, like it's close to 3%. And then we are reporting also the area under the curve as well. And in all these, I mean, it looks like that the model is performing better than these existing tests. Now, the multiple instance learning. So this is where it is taking all these features and then somehow combining them in a systematic way. So if you look at the sensitivity is relatively high, it's close to 74%, and then the specificity, it is close to 68%. I mean, for a machine learning person, it might be, these results might be like pretty bad, because the sensitivity and specificity, they want to see everything in 90s, but that is not possible in all applications. So if we want to compare it, we need to compare it with like the existing methods we have right now, and then the existing method on this particular data set, they are pretty performing pretty modestly. So basically, we are getting a boost of close to like 20 to 30% by using this automatic method. So here are some more results. Here we are combining multiple instance learning versus clinical test. And then again, this Mallampati test and thyromental distance. And again, this sensitivity and specificity of our method, they are pretty close to each other, which also shows that the model is not suffering from any sort of overfitting. So Dr. Segal asked us, can you adjust the sensitivity? Can you make the sensitivity a bit higher, and then you can sacrifice the specificity? And we did that. And even when we did that, the sensitivity is close to like 81%, and the specificity is still above 50%. So it's still better than the other methods, but usually in machine learning, we try to see the sensitivity and specificity at the same level. Okay, so the discussion and conclusions. So the proposed methodology consistently outperforms conventional bedside tests. That is what you have noticed based on these results. There are some areas of improvement. One of them is scaling of phases. So right now, what we are doing is we are taking the phases as it is. So we are cropping regions based off whatever magnification the image has. So the magnification is basically tackled by the CNN. I haven't dig deep into that, but the CNN is taking into account like what magnification is appropriate, and it is making that decision over there. But we still need to start with like putting the images into the network with the same magnification and same scale, and see like if it helps in any way. And we still have to do a thorough analysis of the results. Although these results are good, but we still need to perform an analysis on a larger data set. Facial ratios, like when we have identified these fiducial landmarks, we can identify different facial ratios between different landmarks. We have done that. It doesn't produce good results, but it's still better than the bedside test. It gives you an accuracy around 55 to 60%, but I think it's still reasonable. So we are, at the moment, we are working on the side view images. So we are taking the profile view images of the patient. Dr. Segal has suggested that we should include the neck, so we are including the neck as well. So this is where we are taking it. We're gonna start processing the frontal view and the profile view, and also the neck area, and then see like if we can improve the results somehow. So ultimately, we are thinking about putting together or coming up with a bedside tool. So a clinician could have his cell phone camera, and then they can just snap a picture, and then the computer will tell like if it is easy or difficult to intubate patient. So my last slide is about the funding agency. So the work was supported by Anesthesiology Patient Safety Foundation with Trailblazer Award by NIH, Biomedical Informatics Pilot Award, and the CTSI Pilot Award. Thank you so much. And I would be happy to take any questions. And my apologies for taking longer than anticipated.
Oh, thank you, Khalid, and thank you, Scott. And I know it's almost 6 o'clock in the evening, but thank you for your time. This is fascinating stuff. And I'm sure we'll have a lot of questions afterwards as well when we post these on our YouTube channel. But Piyush has some questions for both of you. I guess this first one is for Dr. Segal. It's about the explainability and interpretability of the work. So if we were to do a large multi-center validation study, would that overcome the issues of explainability and interpretability?
Yeah, it's a great question. I don't think we know the answer yet. I think that one of the nice things, and you know, Khalid didn't tell you all of the different tools and techniques and fascinating experiments that we're doing, but one of the ones we're working on now uses a particular flavor of CNNs called a generative adversarial network that can actually generate facial images by itself that are believable. The analogy is it's a counterfeiter, and it tries to fool another network that is trying to learn the difference between real and fake images, and in so doing, both networks get smarter fast. And the generative side of it could draw faces for us that it predicts are easy or difficult, and we could do sort of, if you will, sorry again with the pun, but face validity testing with human observers, which we already know to have some realistic ability. So people can tell an easy versus a difficult one. And I think it might help build trust if the faces that it thinks are predicted to be easy or difficult are also judged by humans to be the same way. But yeah, sure, a big trial is going to help a lot in a diverse patient population with lots of different people using it, as opposed to just a research tool. So definitely, absolutely, and that will be, you know, if we're lucky, a future grant application to do that large multi-center trial. I think that's right. And Khalid also said, you know, we're a few steps away from really being ready to go with that. I mean, I do think there's a lot of information in the lateral or profile view of the face, particularly as regards some of the stuff that we measure with bedside tests. You know, the thyromental distance, in some people call the sternomental distance, the angle of the neck relative to the axis of the body. Those kinds of things are not as easy to do as frontal facial images, where there's so much open source stuff already finding those features. So Khalid and his team have got a really promising, clever technique now to try to find the relevant portions of a lateral view of the face with a relatively small number of labeled images. And that's actually something we're working on right now. But I think once we get all that in place and maybe include some of the ratios of the positions of different features to each other, as was also suggested in the comments, you know, we should get something that's performing well better than bedside tests, and then it'll be time to try that big trial.
Yeah, no, absolutely. And I guess you touched on the other question that Piyush had asked as well, in terms of breaking the face up into regions. How do we capture the relationship between different regions, and are we losing valuable data there? You know, Khalid, you've already sort of touched on that. I'm going to ask you, Khalid, you know, this coming into all of this, you know, you are not an anesthesiologist. Where do you think all of this is going? And I'm specifically asking you because, you know, as anesthesiologists, we have our vision of where this is going. Where do you think this is going from a purely data science and machine learning perspective?
I think we are pretty close. I mean, we're pretty close to getting a tool, and I think we're going to be providing with like the necessary tools which you require to do these analysis. So we're going to make your life much easier. This is where we are heading. So we want to facilitate you guys and making the diagnosis pretty easy for you guys. And then we want to, I mean, the way I see it is that the healthcare is going to be pretty cheaper in the future. There are some issues like who is going to be responsible if the computer is making a decision and all these things, but I think it's ultimately we're going to overcome all these things, and then we are moving towards like a good healthcare system.
Dr. Segal, is that sort of your vision where all of this is going as well? I don't think this is a automated anesthesiologist. This is just a tool to help, right?
Right, but it's an incremental step, don't you think? I mean, one of the reasons why we bring patients in for preoperative assessment is to do an airway exam. I could certainly see remote airway exams being a very early application of the technology, and only talk to people who are predicted to be difficult, if we can tune the network to be good at that. I also really wonder if helping non-experts is not a bad place to be. Lots of other people besides anesthesiologists manage the airway. I mean, we do a lot, right? But so do intensivists, so do emergency medicine docs, so do paramedics in the field, so do battlefield medics. And I even wonder, we've talked about some other outcomes in addition to difficult intubation, like difficult mask ventilation, obstruction when sedated. We just launched a project to try to predict sleep apnea. There may be other outcomes that can be tied to a rigorous analysis of facial anatomy via the same sort of networks.
Should we be worried about anything in terms of the ethics, the legalities, and so on and so forth of all of this? Just say someday I just have an app on my iPhone, and everyone else, including my 7-year-old, has an app on his iPad where he can point at people and find out how difficult their airway is. Are we going to just make this too complicated for ourselves?
Well, you can envision what any lawyer working for any company trying to market such an app is going to say. There will be all kinds of warnings before you're allowed to even turn the camera on that says this is not a substitute for your judgment, it's an aid to your decision making, et cetera, et cetera. But you know, we do it all the time, Ashish, right? I mean, when you look up at your monitors in the OR, you are not going back and asking, well, I wonder if that strain gauge is actually measuring blood pressure accurately, right? You take it as a thing, and it's a tool to guide your treatment. And I guess that's probably where we're going, but the ethical issues are huge. I think you're right. My 13-year-old just completed a course in artificial intelligence, and they spent a lot of time talking about self-driving cars and whether they should save the people in the car, the people outside the car itself, and how would you design the algorithm in an emergency, and what maneuver should the car take. And I think we'll ultimately have to face questions like that in medicine. Right now, honestly, I think that's way steps down the road. We've got to get algorithms that people trust and show that they actually improve decision making, and then we'll have to face the issues of what do you do when you disagree with the machine.
Sure, great points. Piyush, I know you're here. Everyone else, small group, does anyone else have any other points, questions, remarks? Feel free to turn on your camera or your mics, talk.
I think there is a question in the chat, like if we break the faces into multiple regions, are we going to lose any information?
Yeah, Khalid, if you want to take that, please. I kind of brushed over it.
Yeah, so I haven't like fully explained the method, but there is a part where we are putting the face back together using multiple instance learning. So this is a really good point, and we are trying to preserve as much information as possible by just putting these pieces back together and then taking information from there. But it's a good question. It's a valid point. So the algorithm is doing that at some point.
Excellent. Piyush, do you have any comments for us?
No, I think it was a very exciting thing. I actually have lots of questions. We could do a 2-hour session just going discussing this, but I think for the sake of time, I think you did address some of the key questions. And congratulations on such wonderful work. And looking forward to using your solution in day-to-day life. It's very much needed.
Thank you.
Yeah.
All right, guys, I guess it's time. We're going to wrap up. It's beyond 6 o'clock. Everyone has to go home. So thank you again. This is great. This will be available on our YouTube channel. And if anyone has any comments, questions, you can always shoot an email. Dr. Bathur's email is available on our website as well. And then, stay safe, everyone. Wear your mask where you can, and take care of yourself.
Thank you for the invitation. Good night, everyone.
Take care.
Bye.